this is Dr. Buhler, and because you guys are supposed to do a review of action potentials on your own before class starts, I wanted to give you a little bit of a heads up. Because some of you have different types of texts, I wanted to make sure that you had some way of knowing exactly what it was that you're going to need to know for class. So the neuronal anatomy that you might or might not remember are that neurons are cells in the brain and in the central nervous system, including the spinal cord, and in the motor systems and sensory systems of the autonomic nervous system. They are cells that have a cell body and have a nucleus, mitochondria, just like any other cells. However, they are a little bit different. They have dendrites, which are these processes here, that are the processes that send nerve impulses in to the cell body from other neurons. The soma is a term for the cell body. And then the axon is a process that sends nerve impulses away from the cell body. Those nerve impulses, if you remember, are called action potentials once they get to the axon. So let's remember that dendrites send the information into the cell body, and in the cell body it gets transferred to the axon, in which an action potential moves it down to a synapse. The synapse is going to be the space between the axon of this neuron and the dendrite or soma of another neuron. So that's a little bit easier to see over here, where you have this first cell with the dendrites and the axon. So it's sending the action potential down here. It's releasing at the synapses onto the dendrites of another cell. So that space between those two neurons, is actually called the synapse. You guys might or might not remember the myelin sheath. That is a fatty layer that glia make, and they wrap around the axon, and basically that causes insulation, like in electrical wiring. Only neurons that go a very long distance use that, and that makes sense because if you have a wire that goes a very short distance, you may not need to insulate because you're not going to lose as much information. But if you have a wire going a very long distance, you're going to lose a lot of information and charge. So those long neurons that go from the brain down to the spinal cord, or the spinal cord out to your toe or your hand, are going to have myelin, whereas most of the neurons in the brain itself don't. Now what's released here at the synapse is going to be a neurotransmitter. And a neurotransmitter is any type of chemical that's released onto the next cell for neuronal communication. And so while electrical signals are what the cell uses to communicate within itself, these chemical neurotransmitters are what the cell uses to communicate from the first neuron to the second neuron. Now, one of the important terminologies here that we're going to be dealing with is presynaptic versus postsynaptic. And one of the confusing things is it depends on where you're looking. So if you have a neuron here that has a synapse activating this cell, and then this neuron has a synapse activating this cell, what you call this, presynaptic or postsynaptic, depends on which side you're looking at. So if you start here, this is a presynaptic neuron in yellow. That's going to synapse onto the postsynaptic neuron in purple. But by the time you get over here, the purple one is the presynaptic neuron, and this next one is the postsynaptic neuron. So a neuron really itself isn't pre or postsynaptic. We're just talking about the synapse anatomy itself, whether it's pre or postsynaptic there. So try to remember that on one end, the neuron is always presynaptic. On one end, it's always postsynaptic. On one end, it's always presynaptic. So this is something you're not going to be tested on, but most people, when they're talking about action potentials, really don't understand them. And part of it is because it's talking about electricity, and most of us don't really understand electricity. So I want you to just listen to this. Don't bother taking notes, but just think about this. Electricity, in its basic form, is the flow of charge. So that means a positive or a negative charge is moving. When we talk about wires, we talk about, if this was a section of copper wire, we talk about putting a negative charge in on one side and it moving that charge to come out on the other side. So in wiring, what we do is we move electrons. We inject that negative charge here, and because negative plus a negative charge pushes away another negative charge, right? A negative attracts positive, negative rejects negative. So as you input that negative here, it's going to push away the next one. That negative is going to push away the one after it, and so forth, until the last negative here gets shoved out of the end of the copper wire. And what that was basically electricity, that flow of charge. In copper wiring like this, we're moving electrons. But in neurons, we use ions. Ions from basic chem are just charged atoms. So you can have sodium with a positive charge, potassium with a positive charge, chloride with a negative charge. And since electricity is a flow of charge, if you add in a neuron sodium on one side, it'll push all the positives away and out the other end of the neuron. So remember, ions, which is what we're doing in a neuron, are going to push their neighbors away. So that charge is going to move from the dendrites down to the cell body out through the axons. So why do we need insulation, and what does insulation do? Well, insulation is high resistance. So electrons and ions don't move through it very well. So if we cover this with insulation, I'm going to show you what's going to happen. If you inject the charge here, and say in this wiring example, you're pushing negatives away, what happens if one of these negatives just escapes out here? Well, you're no longer going to have the electrical charge transmission going through the wire. So if these negative ions are just getting shoved out of the wire, you're going to lose signal and you're going to lose electricity. So what we want to do is insulate it. In this example is again a wire, but you can look at neurons and they have that myelin sheath, and that myelin sheath is fatty and it doesn't let charge go through it very well. So as you go down the myelin sheath, the ions can't escape very easily. So it keeps that impulse going well through the neuron itself. So you know what electricity is. And in a neuron, electricity is the movement of ions. That's the movement of charge. So what's voltage? Voltage is any difference in charge between two areas. So in here, for neurons, we're saying the charge on the outside of the neuron versus the charge on the inside of the neuron. So what is the charge on this one? Well, you have more negative ions on the inside than positive, so that's negative charge. And out here you have more positive ions than you have negative, so that's got a positive charge. Show that here as a positive on the outside and a negative on the inside. So that's going to be its cell voltage, or the cell potential, is the difference between these. Because a neuron has a lot more negative charges on the inside than it does on the outside, then that's a negative cell charge. And neurons generally, just by chance, usually have a voltage cell potential of about minus 70 millivolts. So what happens if we open up channels in the membrane to let charges move back and forth? Well, those charges are going to try to equalize, right? If there's more positive here and more negative here, then the negatives are going to flow out and the positives are going to flow in. So it's just like diffusion, except with electricity. So remember, if those ions are moving, and what was the flow of movement of charge? That's electricity. So if a cell opens an ion channel to bring in or kick out ions, that is electricity. So now we're back to, from that review, back to what an action potential is. And that's movement of that electrical charge down the axon. And that electrical charge is maintained by the movement of ions in and out of the axon, in and out of the cell. So again, you have the dendrites, the information coming in to the cell body or the soma, the axon itself, through which the action potential goes down, and then the release of neurotransmitters at the synapse. So that action potential is through the axon is initiated by this being positive, a positive charge that's really created by influx of sodium into the neuron. And every time there's an increased positive on the inside of the neuron, we call that depolarization. So the electrical charge in a neuron is caused by moving charged ions into or out of the neuron. And so that is the electrical charge. The cycle then travels all the way down the axon to the end of the synapse. And you'll remember what you learned in undergrad about the voltage-gated channels and that whole rigmarole about the action potential itself. So let's take a reminder of that. The action potential uses two major channels, the voltage-gated sodium channel and the voltage-gated potassium channel. Here we have an example of the voltage-gated sodium channel, but I haven't drawn out here that potassium channel. Voltage-gated channels, by channel we mean a protein that can open up to let an ion in or out. Usually those proteins are pretty specific. They'll only let in or out sodium, or they'll only let in or out potassium, or let in or out calcium. They generally won't let in and out multiple types of neurons. So when you open a voltage-gated sodium channel, then it's going to open up and let sodium into the neuron, this being the outside of the neuron and this being the inside of the neuron. Voltage-gated means a change in voltage is what causes it to open. So in the case of the action potential, a threshold depolarization, or getting to a positive, more positive voltage on the inside of the cell, is going to activate the opening of that sodium channel. So here we have the sodium channel, it's closed, so sodium cannot get through. Then we have a depolarization, it opens up, and sodium can get through. The interesting thing about sodium channels is they inactivate. So after that opens up and sodium gets in, almost immediately this ball and chain, this little ball sticks in there, and now sodium can't get through anymore. So what's happened is the sodium channel has a way to be closed normally, open up when it's depolarized, and then shut back down again to stop the sodium from keeping to go through. So the sodium channel's quickly activated by depolarization. So as soon as there's a depolarization or influx of positive charges into that cell, it's going to open up. Then it's going to close. Just as it's starting to close, the voltage-gating potassium channel is going to open. That same depolarization at the beginning is opening the potassium channel, but it activates very slowly, so it's kind of lagging behind. So this is what you probably looked at when you saw this in undergrad. You had the action potential drawing here. So we're going to talk about how those individual sodium and potassium channels are actually creating this drawing. This is membrane potential in millivolts. So you can think of that as that voltage in the cell. The cell, I said, starts around -70, can in some neurons be about -60. You go along as you get depolarizations or more positive ions come into the neuron, you reach a thing called the threshold potential. In most cells, that's around -40. It's still negative, but it's less negative. So you had very negative here, you had influx of positive, and now it comes up to about -40, and that's what kicks off those sodium channels. So the sodium channels then open up, potassium channels start to open up, and now those sodium channels completely shut down because of that activation. So those sodium channels are shutting down while the potassium channels are open. Now the sodium channels are totally shut, the potassium channels are open and keep pushing it down. And then you get back to a resting. So let's go through that specifically. You start out in that resting state, and the depolarizing inputs here are going to raise that potential to be more positive. Right now, when you're right here, both channels are closed, sodium channels and potassium channels. It's only until you reach that depolarization threshold that those sodium-potassium channels open. You're going to go up, they're going to open, and what you can see is here, it's the same thing as this picture, except this is the individual sodium and potassium channels, whereas here it's kind of them added together. So you start it up, you hit that depolarization threshold, and now sodium starts to come in, sodium starts to drop off, while the potassium starts to come in. By the time potassium is going to peak, the sodium's channels are pretty much closed. So if you add this together, that's going to basically give you this. Sodium is coming into the cell, potassium is leaving the cell. So with sodium, you're bringing a positive into the cell, so you're depolarizing it, making it more positive. With potassium, you're kicking a positive out of the cell, making the inside of the cell more negative, or hyperpolarizing it. And that's why when the sodium is coming in, you're going to have this more positive. And when the potassium is leaving, you're going to go down to more negative. So during that depolarizing phase, you hit that threshold, the sodium channels open, the potassium channels are still closed. During the repolarization, the sodium channels are refractory, that's our word for inactivated, and the potassium channels are opening. Now you get down here to the hyperpolarizing phase, and the sodium channels are almost completely inactive or refractory, and the potassium channels are still open. So that's why we're going down even more negative than we were before. As we return to the resting potential, most of the sodium channels are closed, and most of the potassium channels are closed too. And so that's what allows us to get back to the resting potential. Now I need to make a really important point, is that sodium channels being closed is not the same as them being inactivated or refractory. Those are two completely different things, and you have to have the terminology right for those. Closed means they're shut and they're able to be opened. Refractory or inactivated means they're shut with that little ball and chain, and you can't open it until it resets. Let's see. Okay, so this is probably what you saw as well. That depolarization then travels down the axon. So that was all happening at one place in the axon. The sodium came in, the potassium went out, you had that membrane voltage change. Now, what happened when it became more positive? Well, just like we were talking about before with the movement of charge, when this becomes more positive inside the cell, it's going to kick positive ions away from it. So in this case, positive comes into the cell. There's sodiums inside the cell anyway, so they push those positive sodiums along, push them along, until they hit here, and now they've made this so positive that it's going to reach threshold and start the whole process over again. This is going to be depolarized. That's going to cause the sodium and potassium channels to open. The sodium is going to cause influx of sodium. The potassium channels are going to cause efflux. And that whole thing is going to send down the axon further and cause the same thing to happen there. So it's going to be jumping back down the axon between the spaces of the myelin sheath. If you don't have a myelin sheath, which a lot of the neurons in the brain don't, then you don't worry about it jumping. You just push along the whole way down the axon. So what was the point of that inactivation or refractory? Well, if you push along the positives here, so now you have positive here, it's pushing those other sodium channels over to here to activate this. There would be nothing to stop it from pushing back that way as well. You have a lot of positive, why doesn't it push both directions? Well, it does. When you reach here and this opens, it pushes positive here and there. You don't want the charge to go backward. You don't want the action potential to go backward. You want to keep it moving forward. So as that positive charge moves forward, it's going to open up the next section. It's going to cause that action potential to move. When that positive charge starts to move backwards, it can't do anything. It can't open this up because those sodium channels are refractory. They're inactivated. So this is a flash that's really interesting, and it kind of shows what the action potential is going to look like. And you should be able to get to it on your version. And so this is going to talk about that sodium channel, that potassium channel. Here's the membrane. So you have the sodium on the outside, the potassium on the inside. And you have those two gates. You don't have to memorize the name of the gates, but remember, this sodium channel is closed right now, not inactivated. That initial gate is closed, and as soon as it opens up, sodiums can come in. Once they come in, that H gate is going to shut, and that's going to stay shut, and that's what makes it refractory. Of course, it'll open up later, but it stays shut for quite some time, milliseconds. So the sodium's going to get high here. It's going to come into the M gate. It's going to go through. At the same time, potassium channel is going to open, but it's going to open slower. Potassium is going to go out. So as we go, you can see here what's going to happen to the voltage. At the beginning, when the sodium channel is open, voltage is going to get more positive. At the end, as the potassium channel is open and the sodium close, it's going to get more negative. So let's go ahead and start. So now the sodium channel opens, sodium comes in, and then closes refractory. Potassium channel opens, potassium goes out, and you come down here, and now it resets. Try that again. Is it going to do it? No. Okay, so we're starting along. We get some ion depolarization that causes sodium channel to open. It shuts, potassium goes out. You get that hyperpolarization, and then it comes back to normal. So we talked about that myelin. We don't need to go into great detail about the myelin. We've already probably learned about it. The glial cells wrap those axons in that fatty layer. The myelin increases the resistance along the membrane, and that was so that the charge can't just escape, so that the charge as it gets pushed along keeps being pushed along the axon instead of just dissipating out. That's going to make action potentials go further and faster. And that's what we want when we have a neuron that goes a very long way. We don't want slow action potentials that might just kind of burn out if we need to get information from our brain down the spinal cord to our legs. So one of the problems in multiple sclerosis, and you're not going to be tested on this right now, but it's kind of an interesting example of why we need myelin. Multiple sclerosis is an autoimmune disease in which myelin gets attacked. And so when that myelin gets attacked on neurons, all of a sudden they start losing their signal. And so that electrical signal starts just diffusing out of the cells, and it doesn't move down as fast and it doesn't move down as efficiently. So you start losing neuronal signaling down. And so in multiple sclerosis, what you can see is deficits in movement and deficits in sensory functions. So the learning objectives for this are going to be based on this lecture, which should just be a review of the information you had before. You want to understand the physiology and steps of this generation of action potentials. You want to describe postsynaptic action potential generation. You want to identify the voltage-gated ion channels, sodium and potassium. You want to know what activates them. That's going to be depolarization. You want to know which ion is involved in each. Sodium and potassium channels should be a good clue. And you want to know whether it's hyperpolarizing or depolarizing. So the influx of sodium is depolarizing. The efflux or sending out of potassium is hyperpolarizing. You're going to want to know the 5 steps of the action potential. Those were shown on one of the previous slides. You need to know the difference between open and inactivated for sodium channels, and be able to describe what inactivated means and why that's different than open. You want to know for each step what's going on with the cell in terms of its voltage. Is it resting? Is it depolarized, hyperpolarized? And know that in those last steps, 4 and 5 of the action potential, those sodium channels are refractory. And you can want to be able to discuss why that matters on the way that action potentials move. And then fairly simply the effect of myelin on action potentials. And you don't really need to be able to talk about multiple sclerosis, you just want to be able to talk about why myelin is useful and the physiological effects. So I hope that this review helps you out a little bit and gets you ready for day 1 of CNS.